In this lecture, we'll take a look at the concept elementary row operation and row equivalent matrices. So let's say that we have an arbitrary matrix A, it's n by m. Whenever I pre-multiply a matrix by an elementary matrix, we say that we perform an elementary row operation on A. So there are three elementary row operations that we can perform on a matrix. Swap two rows, scale a row, and pivot a row. That is, add a multiple of one row to another. If you post multiply a matrix A by an elementary matrix, we say that we perform an elementary column operation on A. It's not hard to understand why they are called elementary row and column operations. Here I have a matrix A, which is 4 by 3. When I pre-multiply by an elementary matrix, in this case an elementary matrix of type 1, I am performing an elementary row operation on A. And it's called row operation because it affects rows. In this case, it swaps rows 1 and 2. Here I'm post multiplying by an elementary matrix, so here I'm performing an elementary column operation on A. It gets its name because it affects the columns of A, in this case swapping column 1 with column 2. So once I have performed an elementary row operation on a matrix, I will have a new matrix of exactly the same dimension. On this new matrix, we can actually perform additional row operations. That is, we can perform several row operations on a matrix. Here's an example. I have a 3 by 3 matrix A, and I have two elementary matrices. The first one is of type 2, multiplying the entire row 1 by -1. The second one is of type 1, swapping rows 1 and 2. If I now do E2 times E1 times A, that is the same thing as performing two elementary row operations on A. We know that when we do E1 times A, the effect will be that the first row is multiplied by -1. And when we then do E2 times that result, the effect will be to swap the first and the second row. In this example, I began by doing the product E1 times A, but remember that matrix multiplication is associative, so it's not necessary to have a parenthesis around E1 times A, because you will get exactly the same result if you begin by doing the multiplication E2 times E1 and then multiply that by A. Here's another example. A is a 3 by 3 matrix. Let's perform a sequence of elementary row operations on A such that the first column becomes 1, 0, 0. The first thing we can do is to turn the 6 in 2, 1 into a 0. That we can do with the following pivot matrix. It's 3 by 3, it will affect row 2, it will use row 1, and it will add -3 times row 1 to row 2, making element 2, 1 into 0. Let's call the result A1, and we can see that A1 has exactly 0 at position 2, 1. Next, let's get rid of this 7 in position 3, 1. To do that, we use the following swap matrix. And the product will be called A2, and now A2 has zeros in column 1, row 2 and 3. And the final thing we need to do, if I want to transform the first column into 1, 0, 0, is to multiply the first row by a half. So then we need this scale matrix E3. And let's call the final matrix A3, and A3 has as its first column precisely what we wanted. And so the idea is that you can perform all these row operations in one step. If you start with your A matrix and you do E3 times E2 times E1 times A, you will immediately end up with a matrix which has 1, 0, 0 as its first column. So by performing a sequence of elementary row operations on a matrix, we can transform it into a very different matrix. And an extremely important question is whether you can actually transform it into the identity matrix. We'll see that sometimes you can, sometimes you cannot. Pretty much everything we say about elementary row operations apply to elementary column operations as well. So you can perform a whole sequence of those as well. Next, we have the concept of row equivalence of matrices. So let's start with an arbitrary n by m matrix A. We say that this matrix is row equivalent to another matrix B, which is also n by m, if A can be transformed into B using elementary row operations. Sometimes you can, and sometimes you cannot. We'll look at examples. So the idea is that I start with the matrix A, I pre-multiply by an elementary matrix called E1. Then I can do it again. So I do E2 times E1 times A, and again, trying to get to B. If I eventually get to B, by pre-multiplying by a sequence of elementary matrices, then we say that A is row equivalent to B. That is, if I can find a number of elementary matrices, let's say I need P of them, such that once I have pre-multiplied by E1, E2, E3, all the way to the final EP, I end up with B, then we say that the matrices are row equivalent. Trying to determine if two given matrices are row equivalent or not is important, and it turns out not to be very difficult. So here's an example based on the previous slide. I started with A. I performed two elementary row operations on A. I multiply the first row by -1, and then I swap the first and the second row. Then I ended up with the matrix B, so that means that A must be row equivalent to B. Keep in mind that if A is row equivalent to B, then these elementary matrices are not unique. There might be many ways of getting from A to B. And we can define column equivalence as well, simply by doing a sequence of post multiplications instead. Finally, we have some important results on row equivalence. First, row equivalence forms what's called an equivalence class. That really means the following. Let's say that A, B, and C are three arbitrary matrices of the same dimension. First, A is row equivalent to itself. That follows from two facts. The first is that the identity matrix is an elementary matrix. Second, if you pre-multiply A by the identity matrix, you end up with A itself. So you can get from A to A simply by pre-multiplying by the identity matrix. Next, if A is row equivalent to B, that is, you can get from A to B by performing row operations on A. Well, in that case, B must be row equivalent to A. And to go from B to A, you simply need to perform the opposite elementary row operations on B. A formal proof in an exercise later. And finally, if A is row equivalent to B and B is row equivalent to C, then A must be row equivalent to C. It's called transitivity. Again, the basic idea is that to go from A to C, you first take all the elementary matrices that you need to go from A to B, and in front of those you stick all the elementary matrices that you need to go from B to C. And that will take you from A to C. An example later on will probably clarify this. Here is one of the most important results related to the inverse of a matrix. If A is a square matrix, keep in mind that elementary row operations and row equivalence applies to non-square matrices as well. But in this bullet point, A is a square matrix. Then A will be row equivalent to the identity matrix if and only if A is invertible. Here's an example, 2 by 2 matrix. It's invertible with this inverse, and that means that A must be row equivalent to the identity matrix. In this case, it's fairly straightforward to find the elementary row operations that will take A into the identity matrix. We can begin by getting rid of the 6 at 2, 1 by adding minus 6 over 7 times the first row to the second, like this. Then we can get rid of the 3 in 1, 2. In this case, by adding to the first row minus 3 divided by 4.428571 times the second row, like this. And the final two steps is simply to scale the first row by 1 over 7 and the second row by 1 over 4.428571. That will turn it into the identity matrix. On the other hand, consider the following matrix A. If you try to invert this, it will not work. This does not have an inverse. It's not hard to show that there is no matrix such that A multiplied by such a matrix will give you the identity matrix. And since it's not invertible, we know that it cannot be row equivalent to the identity matrix. That too is quite clear. It's very close to the identity matrix already. What's incorrect is the 0 in 2, 2. That should be 1. But there is absolutely no way to perform an elementary row operation making that 0 into a 1. If I add a multiple of the first row to the second, it's not going to make any difference. A multiple times 0 will always be 0, so that will add 0 to 2, 2. I can't scale the second row. Multiplying the second row by any constant different from 0 will still make it into 0. And the swap will not work. If I swap these two rows, I'm actually further away from the identity matrix. But there is nothing I can do to the second column to make one of those elements into a 1. And so it's not invertible. The proof of this result is quite important and instructive, so you should probably check out that exercise which deals with this proof. Finally, two invertible matrices must be row equivalent. Why? Well, if A is invertible, then we know from the previous bullet that it's row equivalent to the identity matrix. Similarly for B, since B is row equivalent to I is row equivalent to B. So we have A is row equivalent to I, and I is row equivalent to B. Then from transitivity, the third dash in the first bullet, it follows that A must be row equivalent to B. Similarly, if you have two matrices, one being invertible and one not, then they cannot be row equivalent. However, if you have two matrices, neither of them being invertible, then they may or may not be row equivalent. For example, these two matrices are row equivalent, just swapping rows 1 and 2, while C and D, both being non-invertible, are not row equivalent. There is no elementary row operation that you can do on C to get to D and vice versa.